Welcome to PCI ELT 122 DC Electronics 2 class. My name is Steven Seipkins and I will be going over the lectures in this class. Today's lecture is the week 1 lecture on series parallel circuits, and we will get started. If you look in your book, the first diagram in section 1 is a series parallel circuit right here with 4 resistors in it. Your first task in series parallel circuits is to find R total. And to do that, you have to be able to identify which of these resistors are in series and which ones are in parallel. The ones in series you can tell because there is no alternate path. The electrons have to flow through both electrons and they have no choice. So between R1 and R2, because there is no choice, that is series. And so we will solve this part, combine these two resistors using series equations. If you notice R3 and R4, there's a chance I have an alternate path between these two. So R3 and R4 are in parallel because they are two separate paths. The electrons come here and they have a choice, and they have a choice to go that way or that way. That makes it parallel. Again, the top and the bottom are connected to the top of the resistors and the bottom of the resistors. That's a parallel circuit. Some people get confused by these. They think R2 and R3 are in parallel. But they are not, because there's a choice here, right? Electrons have a choice of going one way or the other. That prevents R2 and R3 from being in series. They are not. R1 and R2 are in series. R3 and R4 are in parallel. And you must be able to determine that before you can solve a series parallel circuit. Because the first thing you must solve is the total resistance. So going with that, R1 and R2 in series, we're going to solve this in 4 steps, and this is done until you get good at simplifying these. So, again, series circuits, you combine the resistance by adding them together. So, R12 equals R1 plus R2. In series, we add our resistors. And so I have 0.5K for R1 ohms, plus 0.5K for R2, and so if you add those together, R1, 2 equals 1K ohms. 0.5 plus 0.5 equals 1K, or 1,000 ohms. Again, we use the comma between them when we combine these, so this is resistor 1, 2, which basically specifies that we have combined these two resistors into an equivalent resistor. We come over here, and so this is our updated drawing. We've simplified R12, and since we've simplified it, we now have a new circuit. So R12 is now 1K ohms, and we can act off this circuit. So we've simplified the first 2 resistors. The next resistors we simplified, do we have a pure series or a pure parallel? We don't have a pure series, but R3 and R4 are a pure parallel. And so we're going to simplify that. And they are equal. And so in resistance, when you have equal parallel resistors, you could use the shortcut, which is that R3, 4 will equal your resistance value divided by the number that are equal in parallel. In this case, R will equal 1K ohm, or 1,000 ohms, and the number in parallel is 2. So 1,000 ohms divided by 2 is 500 ohms, or 0.5 K ohms. So that simplifies R34 into a 0.5 K ohm resistor. So now we come over here, we have our third sequence updated, simplifying it down. R34 is 0.5 K ohms. R12 again was 1 K ohm. And now that we've simplified it into 2 resistors, you've noticed these 2 resistors are in series. There's only one path. So we're going to simplify this last combination into a single resistor. That's what we have to do in series parallel to come up with total resistance. We must simplify all the resistors down to a single resistance. And so R12 in series with R34, we're going to add that. So our R1, 2, 3, 4 is equal to 1K ohms for R12 plus 0.5 k ohms for R34. And that gives us an R1234 equal to 1.5 k ohms, or our total. This is our answer for this, and this is the first step in solving any series parallel circuit, is to combine all the resistances into an equivalent resistance, and 1.5 k ohms is the equivalent resistance of this circuit. So that's our first step. That's the first thing you have to do. What you would do from here then is solve for your total current. Since our R total, we know now, is 1.5 k ohms, which is 1,500 ohms, 1,500 ohms, we can solve for I total using Ohm's law. And if you remember your Ohm's law circle, current equal voltage divided by resistance. So this will be voltage total divided by resistance total, which is 1.5 volts divided by 1.5 k ohms. And so you take your calculator, your TI 30XA, right? You enter in 1.5, you divide it by, enter 1.5, hit your E button, and K is times 10 to the third, you hit 3, hit equal, and you end up with, on your calculator, 0.001 amps or 1 milliamp. Equals 0.001 amps, which equals 1 milliamp. So now we know our I total. Okay. If we're going to solve this the rest of the way, and we don't do that in the first step here, we'll do that in the later sections, but I'm going to show you how you would solve the rest of this for voltage drops. You take that current from the top of the battery, the positive part of the battery, you come around. Since there's only one path through here, that whole 1 milliamps goes through that series path, right? Which means IR1 is equal to 1 milliamp, and IR2 is also equal to 1 milliamp, because all that current has to flow through both those resistors. Okay? So we know the first two currents going through. Since I have current and resistance on those first two resistors, I can solve for my voltage drops. VR1 is going to equal IR1 times R1. That's just Ohm's law. Voltage, Ohm's law works on every resistor. I know the current on the first resistor and the resistance on the first resistor, so I can solve for the voltage on the first resistor. And this is 1 milliamp times 0.5 k ohms, and that's just going to equal 0.5 volts or 500 millivolts. That's my VR1. That's my voltage drop on the first resistor. VR2 is going to be the same equation. VR2 is going to equal IR2 times R2. It's the same values, 1 milliamp times 0.5 k ohms. So it's also going to be 500 millivolts. That gets us to the first node. And there's something you need to know about nodes. Kirchhoff, who did Kirchhoff's voltage law when you studied your series circuit, did something for parallel, series parallel, which was Kirchhoff's current law, which says all the current entering a node is equal to all the current leaving a node. Since we know the current coming in, we know we have 1 milliamp coming in. There's a shortcut here. Since we know these resistances are equal, we know they will split that current equally. So this is a shortcut. Basically, I'm going to have 0.5 milliamps going down, or half of that current is going to go down, and 0.5 milliamps is going to come over here through R4. So half the current goes down, half the current goes through R4. So now we know IR3 equals 0.5 milliamps, and IR4 equals 0.5 milliamps. And if we solve for VR3, which is Ohm's law, IR3 times R3, That's going to be 1K times 0.5 milliamps. That's going to be, on your calculator, that'll end up being 500 millivolts. And VR4, same values. IR4 times R4 is also going to be 500 millivolts. You can check your work on this by understanding Kirchhoff's voltage law. Kirchhoff's voltage law, if you remember, said that all the voltage in a loop will equal 0, which means I take my 1.5 volts, and if I subtract all the voltage drops in one loop, I should be 0. So we started with 1.5 volts on the battery. We drop 0.5 volts here, 500 millivolts is 0.5 volts. That leaves us with 1. We drop another 0.5 volts. That leaves us with 0.5. And we drop the last 0.5 volts here, and we end up with 0. So we dropped all our voltage in that loop. There's also a loop here through the back end. It also must equal 0, and it does. 1.5 volts minus 0.5, minus 0.5, minus 0.5, and I have 0 volts. So we have solved everything in this problem. So that finishes the first section. I highly recommend you do the self-review questions for your own learning and own practice, and all of this should help you with your homework for the week.